Hi students, welcome to Max Point of View. Today we are going to solve each and every previous year questions from the chapter Calorimetry. Before watching this video, my suggestion is watch the concept video, theory solutions of this chapter, then come back to this video because few concepts and few terms will definitely confuse you. If you have prior knowledge, solving these previous year papers will be very easy for us. We are going to start from 2017 to 2025. Why not before 2017? Because before 2017 the syllabus was completely different and easy questions were more than the logical questions. Now logical questions are more, direct questions are less. Finally, why you have to watch these previous year solutions from maths point of view? The first reason is there are many websites will give you the answers for previous year questions, correct? So different websites will give you different answer. We don't know which is correct. Here we are going to give you proper and analyzed answer from the textbook. And the second reason is if the answer is correct in some other websites, we don't know how to understand it because there is no one to teach it. Here we are going to teach it properly and we will make you understand how we got this answer. And third reason is they will give you the solution. You will understand, sometimes you will understand, sometimes you will by heart. Or what if the question is changed? What if the question is twisted in a different way? In maths point of view, we will take the same question, we will twist it in all possible ways so that if the same question is twisted in different ways in the board exams, you will be able to answer it. These are the main reasons why you have to watch the videos of maths point of view. We will teach you in all the possible ways so that you can attend the board exam with the confidence. So without wasting any time, we'll start with our first question. Before going to the questions, my suggestion is watch the concept video, theory solution and numericals because without basic knowledge we cannot solve previous year questions. So now we'll start with our first question from 2017. Define heat capacity and state its SI unit. Okay, heat capacity. Remember, heat capacity has one more name, that is thermal capacity. They can ask you thermal capacity or heat capacity, both are same. And there is a small difference between heat capacity and specific heat capacity. So what is the difference? That is what we are going to learn. First we will try to define what is heat capacity. Okay, the energy required, okay, the amount of energy required to raise the temperature of an object by 1 degree Celsius or 1 Kelvin. See, to raise the temperature by 1 degree Celsius or 1 Kelvin, how much energy is required? This is heat capacity. Okay, now we'll talk about specific heat capacity. See, this specific heat capacity is not asked in this question, but we need to understand because we cannot expect the same question in the exam, right? So the small difference is you need to add unit mass in the definition. The definition, the exact definition remains same. We are going to add unit mass. So what is the difference between heat capacity and specific heat capacity? Heat capacity is about the complete mass of an object. Okay, so how much energy is required to raise the temperature by 1 degree Celsius for the complete mass of an object. If the mass is 5 kg, we'll calculate it for 5 kg. But specific heat capacity will calculate it for unit mass. Unit mass means 1 gram or 1 kg. That's it. This is main difference between heat capacity and specific heat capacity, and they are looking for SI unit also, correct? So SI unit of heat capacity, see, C dash represents heat capacity. Keep this in mind. C dash represents heat capacity. So for C dash, SI unit is joules per Kelvin. Joules per Kelvin, or you can write joules per degree Celsius. Any one is fine. Okay, so most of the time in numericals they'll use joules per Kelvin, but sometimes they can also use joules per degree Celsius. Both are same. Few students will be confused with Kelvin and degree Celsius. Here we are not converting it. Okay, I'm telling per Kelvin and per degree Celsius both are same. Here we are not converting it. Keep that in mind. Okay, see, I'll give you one example. 274 Kelvin, that means 1 degree Celsius, correct. 275 Kelvin is equal to 2 degree Celsius. Now what is the difference here? 1. What is the difference here? 1. That means for every 1 degree rise in Celsius, 1 Kelvin will also increase. So if degree Celsius increases by 25, Kelvin also increases by 25. We are not converting it, we are just checking the delta T. Delta T means change in temperature. So if 20 degree change in temperature, 20 degree Kelvin will also change. That is, in that way we are saying joules per Kelvin is equal to joules per degree Celsius. So it is not conversions. Next, if they ask you, okay, specific heat capacity, the definition is done, we need to go for SI unit also. Specific heat capacity is C. C dash represents heat capacity or thermal capacity. Then, so SI unit will be joules per kg per Kelvin. So what is the difference between specific heat capacity and heat capacity? Heat capacity is for the complete mass of an object. Specific heat capacity is for unit mass. Unit mass is nothing but 1 kg or 1 Kelvin. So this kg is the SI unit, right? That's why I'm writing kg. If you write gram here, completely wrong. If they are talking about specific heat capacity and its SI unit, if you write joules per gram per Kelvin, completely wrong, because gram is not the SI unit, kg is the SI unit. So this is the definitions and these are the SI units. In this question they have asked only heat capacity, but we should know the difference between heat and specific heat capacity. And what is another name for heat capacity? Thermal capacity. Our next question, why is the base of a cooking pan generally made thick? See this question, and I'll tell you one more question, that is, why is the base of the iron box is made thicker? For both the questions answer remains same. Here they are talking about cooking pan, they may ask you about anything. Okay, why it has to be thicker? The answer is very simple. See, in order to increase the heat capacity or thermal capacity. So in order to increase the heat capacity or thermal capacity, what is the use of it? If we made it thicker, heat capacity increases. After cooking, it keeps the food warm for a longer time. This is the advantage. If it is thinner, okay, after cooking it will not keep the food warmer for a longer time. If it is thicker, it keeps the food warmer for longer time. This is the advantage. Our next question, state whether the specific heat capacity of a substance remains same when from solid to liquid. Give one example to support your answer. So that they are simply asking whether the specific heat capacity remains same or it will change when there is a change in state of matter from solid to liquid, liquid to gas. If anything changes, okay, any state of matter changes, will the specific heat capacity changes or not? That is their question. We have learned this one in the concept video. The simple answer is no. Keep this in mind. So for solid to liquid or liquid to solid, any change of state matter takes place, specific heat capacity also changes. It will never remain same. Keep this in mind. Okay, so they are asking yes or no question, right? So right now specific heat capacity will not remain same. If you want to conclude it, if you write no, that is also fine. So next, and give an example to support your answer. We know, see, what is the symbol for specific heat capacity? C. C of per gram per Kelvin. See here, in all the three cases we are talking about different forms of water. Okay, water as a liquid, water as a solid, water as a steam. Correct. In all the three states of matter, specific heat capacity is different. But in the exam, you don't have to write all the three. If you write any two, that is fine. Okay, so specific heat capacity of water is 4.2 joules and specific heat capacity of ice is 2.1 joules per gram per Kelvin. Unit also plays a major role, because if the values are correct and if the units are wrong, okay, then definitely you will lose marks. In our school, whenever we conduct exams, okay, whenever students write correct value or when they calculate correct value, if they don't write units, you will obviously lose mark. Assume there is a 4 mark question. Okay, all the 4 sub questions have some calculation. In all the 4 sub questions, values are correct. In all the 4 sub questions, units are wrong. You will lose all the 4 marks. That is why in physics, okay, that to ICSE, units plays very much important. In CBSE state also unit plays important, but here it carries 1 mark. If that is wrong, easily you will lose 1 mark. That is why always focus on units also. See, practice is the key. If you just see and come and the calculations, units and all, you will never write it properly in the exam. So always practice it, because while practicing it you will make mistake and you can easily recover in the home, but during the exam you cannot recover. That is the problem. So practice and go for the exam. Our next question: how is the transfer of heat energy by radiation prevented in calorimeter? See, when it comes to calorimeter, in the theory concept, we have learned 5 give reason type of questions. Okay, when it comes to calorimeter, there are 5 give reason type of questions. That is what we have learned in the concept video. That is why I'll always suggest you watch the concept video, theory, numericals, everything, and come back to the previous year paper. So here, out of 5, one question is asked. Okay, how is the transfer of heat energy by radiation is prevented? Very simple, by polishing the inner and outer surface of the calorimeter. This is the answer for that question, sub question A. We have one more sub question B. You have a choice of 3 metals A, B and C of specific heat capacity is 900 joules per kg per degree Celsius, 380 and 460 respectively. To make the calorimeter, which material will we select? Justify your answer. See, first we need to understand, we are talking about calorimeter, material of the calorimeter. Generally it is made up of copper, correct? Generally it is made up of copper. Why we have to say take copper? That too, we need to take copper, thin sheet of copper, correct? Thin sheet of copper vessel, correct? Why we have to take copper? Because it is a good conductor. If it is a good conductor, its specific heat capacity is low. This is very much important. Good conductors will have specific heat capacity low specific heat capacity. Poor conductors like water, if you take copper and water, which will conduct heat energy more, this one copper, correct? But water will also conduct, but it will take lot of time. But when it comes to specific heat capacity, good conductor copper, okay, copper has less specific heat capacity, and water, okay, it is a poor conductor, it has more specific heat capacity. So here we got to know, to select a calorimeter, it has to have less specific heat capacity. Out of 900, 380 and 460 joules per kg per Celsius, which one we have to select? Metal B, or metal with 380 joules per kg per degree Celsius. So answer for A is done. B, metal B. Okay, metal B. If you write B also, that is enough. They will give you full marks. See, you don't have to write metal. If you write B, you will get full marks. If you write 380 joules per kg per degree Celsius, if you write that's it, you will get full marks. Then we have to justify your answer. We have selected the metal. Now we have to tell them why we have selected this metal. Very simple. If the calorimeter has less specific heat capacity, it absorbs less heat energy from the liquid. If you write this much, you will get full marks. That is why always we select metal with low specific heat capacity. If the specific heat capacity is low, it absorbs less heat energy. That's it. Our next question: name 2 factors on which the heat energy liberated by a body depends. See, they are talking about heat energy liberated. What do you mean by heat energy liberated? Liberated means it is giving out the heat energy. If the same question asked in a different way, then answer remains same. So what is the different question? Name the 2 factors or 3 factors which the heat energy absorbed by a body. whether it is absorbing heat energy or liberating heat energy, the factors remain same. Okay, while if the heat energy is going out or coming into your body, then the factors remain same, so they can change any question. You have to be very careful to answer these kind of questions. If you know the concept, aramse you can answer. They're asking for 2 factors, we will go for 3 factors, all the 3 factors which is stated in the textbook. First one, mass of the body. Okay, mass of the body is directly proportional. So this is the main advantage when you watch videos from maths point of view. If you search this question in Google, it will definitely give you proper answer. But whether it is directly proportional, extra knowledge, who will give you? So videos will explain. We are explaining the concept, you will understand properly. So mass of the body. If the mass of the body is more, it absorbs more heat energy or it liberates more heat energy. Keep that in mind. Okay, if the mass of the body is more, it absorbs more heat energy or it liberates. Liberate means it gives out more heat energy. So it is directly proportional. Then, but the reason, if the mass is more, it absorbs more energy, all those things they are not asking. But if they ask how the mass of the body is related to heat energy absorbed or liberated by a body, if that is the question, you have to write more the mass, it absorbs or it liberates more heat energy. Then temperature of the okay, so temperature of the body, how it is related? It is again directly proportional. More the temperature you want, it absorbs more heat energy. If you keep on more temperature to a substance, it keeps on absorbing more heat energy. So temperature of the body and heat energy absorbed or heat energy liberated, both are directly proportional. Then material. Okay, what do you mean by material? Different material absorbs or liberates different amount of heat energy. See, iron will absorb or liberate more heat energy compared to other metal, correct? So it depends upon the material, or you can write it as specific heat capacity. See, I will write it in short form, you have to write it in full form. Material, different material, or specific heat capacities of different material are different. So based on specific heat capacity, it absorbs or liberates more or less heat energy. So these are the 3 factors. They are asking for only 2, you can write any 2. That's it. Our next question, calculate the mass of ice needed to cool 150 gram of water contained in a calorimeter of mass 50 gram at 32 degrees Celsius such that final temperature is 5 degrees Celsius. Specific heat capacity of calorimeter, water and latent heat of ice is given. See, first here when it comes to these kind of calculations, we have learnt a method. Okay, in the numerical video I have taught you a proper method. Left hand side hot objects, right hand side cold objects. Okay, so if you write these one, that is nothing but heat lost by an object. Hot object is always going to lose the heat energy, correct? Heat lost by an object is equal to heat gained by an object. This is the principle of calorimeter, correct? What is the principle of calorimeter? Heat lost by an object is equal to the heat gained by the object. Okay, now here that is the principle. Now in order to first we'll write down the given data, then I'll teach you how to solve it. First, so hot object, always take hot object as the object 1, M1, T1, everything should be related to hot object. Then M2, C2, all those things are related to cold object. So according to the question, M1, see what is the hot object? What we are doing, we are adding ice to cool the water. So ice and normal water, which is hot or warm water, correct? So we'll take water as M1, so that is nothing but 150 gram. Okay, M1 always related to, if you keep this in mind, then you will not have any confusion. You can take ice as M1, anything is fine, but if you follow a procedure when it comes to calorimeter, it will definitely help you. So object 1 is always hot object, keep that in mind, then it will be easy for us. So whatever is related to M1, I'll write it here. See, 150 gram of water contained in a calorimeter of mass. the mass of what? Calorimeter. So MC, mass of calorimeter, is 50 gram. Then at 32 degrees Celsius, what is the present temperature of calorimeter as well as the water? That is, okay, 32 degree Celsius. 32 degree Celsius. Now this is the present temperature, and the final temperature is, okay, that is final temperature, not T2. Final temperature is always represented at just T, that is 5 degree Celsius. Then we are talking about adding ice, correct? Whenever we add ice we know the temperature is 0 degree Celsius. So T2 is equal to 0 degree Celsius. This we need to know. So that will not be mentioned in the question, that we should know. Okay, mass hot object, mass of calorimeter, okay, then T1 of both, because water is in calorimeter, correct? We put water in the calorimeter, so these two will have the same temperature and these two will come to the same final temperature. Then what we are adding? We are adding ice. What is the temperature of ice? That is 0 degree Celsius. This we should know. And the water symbols, see, capital C we use, that is specific heat capacity, capital L specific latent heat. Okay, so here C, just C means specific heat capacity of water. Specific heat capacity of water, that is 4.2 joules per gram. This is very much important. Okay, see, if the specific heat capacity is in kg, okay, see, specific heat capacity of water is given in terms of grams, correct? So if this is in kg, all these values should be in kg. Keep this in mind. If this is in grams, the everything should be in grams, so there will be no conversions here. Okay, so that is important. If this is in gram, all the mass value should be in grams. If this is in kg, everything should be in kg. Or else if this is in gram, convert the specific heat capacity into grams. If they are given in kg, if this value is given in kg, convert into grams, then if everything is in gram, that is always fine. If this is in kg and this is in grams, everything will be wrong. Keep this in mind. Next, specific heat capacity of water is done. Specific heat capacity of calorimeter, that is 0.4. Then specific latent heat capacity of ice, that is capital L, that is 330 joules per gram. Okay, these are the given data. Now we know, according to the principle of calorimetry, heat energy lost by an object is equal to the heat energy gained by another object, correct? So whenever you are adding ice to water, which is losing the heat energy? Ice already has less heat energy, correct? So which is losing it? Water is losing it, ice is gaining it, because once ice gain the heat energy, it will get melted, correct? That we need to know. So these kind of numericals we have already solved. So heat energy lost, that is by calorimeter as well as the water will lose the heat energy. So what is the formula? M1 CW T1 minus T plus mass of calorimeter, CC of calorimeter, and same temperature is equal to ml. See, this is the specific latent heat. Once we add ice, after few minutes, okay, it will melt. Again, it will convert into water. That is why specific mass of the ice, specific heat capacity of melted ice, that becomes water. Then temperature will be T minus T2. This is very much important. Okay, so this is the main formula. Here we have all the values except this mass. Okay, then we substitute it. Here you can take m as common, L plus CW, okay, T minus T2. So okay, this remains same, and substitute the values. Well, first now we'll substitute. I'll write this one as it is. Okay, how we got to know all these things? This lengthy formula, all these things we have learnt in the numerical concept. That is why we are not learning here. We are just solving previous year papers. Now substitute all the values. M1 155 is equal to M. Okay. If you want M, you send all these things here. So if you send all these things here, it becomes denominator. Mass of ice only we have to find, right? So this is the mass of ice. Then if you send everything here, it becomes, what is L? That is 330 plus CW. CW's specific heat capacity of water, that is 4.2. Then T minus T2. So what is T? That is 5 minus 0. So if you solve all these things, you will get the mass as 50 grams. That's it. So here the important thing, see, in the exam, how these kind of questions are evaluated. Very simple. These questions will be asked for 3 marks. For the left hand side substitution, 1 mark you will get. Right hand side substitution, 2 marks. So if this question is for 3 mark, you are going to get 2 marks just for substitution. This is only possible in calorimetry. In calorimetry numericals, if you just substitute both everything properly, you will get 2 marks. In everywhere, okay, in everywhere in physics and ICSE physics, you will get 1 mark for substitution, but only in calorimetry, LHS and RHS substitution, proper substitution. See here, this one is called as substitution, not this one. Okay, not the second step. These values, substituting the values will carry 2 marks. Then getting the final answer is that is only for 1 mark. So calculation and all we don't care. Substitute, write the answer directly, done. Okay, so this is how we evaluate in the exam. Be careful with the calorimetry substitution. Now we'll move on to 2018. In that first question, how can a temperature in degrees Celsius be converted into SI unit of temperature? What is the SI unit of temperature? Kelvin. Correct. So they are asking us to convert asking us to write the formula to convert from degrees Celsius to Kelvin. So this question is all about degree Celsius to Kelvin. See, very simple. K is equal to C plus 273. That's it. Okay. C plus 273. If you assume the present temperature is 27 degrees Celsius. 27 degree Celsius. Okay. 27 degrees Celsius. How we can convert into Kelvin? We'll add it with 273, right? So to find it in Kelvin, this is an example which is not asked in the exam. This is for your reference. 27 plus 273, this becomes 300 Kelvin. That's it. This is one example. Okay. Next, we have one more sub question. A liquid X, we don't know that X is a liquid, as the maximum specific heat capacity. It has a maximum specific heat capacity. That means it is a poor conductor of heat. Keep this in mind. Poor conductor of heat has more specific heat capacity. Good conductors will have low specific heat capacity. And it is used as a coolant in a car radiator. Radiator, it is a part of an engine. To cool it, we are using a coolant, a liquid. What is that liquid? See, whenever they talk about coolant, okay, some liquid to cool anything, okay, that is nothing but water only. So answer is water. What is that liquid X? That is water. To reduce the temperature of an part, we may there will be a tube. In that tube, if you run a normal water, this water will absorb heat energy. If the object temperature is more, if you run a cool water, okay, or normal water, it absorbs heat energy, so the temperature will be reduced. So what is that liquid? Water. That's it. Our next question, heat supplied to a solid changes into liquid. What is this change in phase called? So here you have to be very careful. They are generally asking the name, correct? If they give you the exact example, then answer will be different. So here general answer, this is what we have learned from 6th standard, correct? Solid to liquid. The answer is melting. If they take an example of ice to water, ice to water, then the answer will be latent heat of fusion. See, they are not going specifically, correct? Ice to water, then answer will become latent heat of fusion. What do you mean by fusion? Fusion is nothing but melting. So if they go specifically, you have to write latent heat of fusion. And what if they, okay, if the water is converted into ice, then that becomes latent heat of freezing. Latent heat of freezing. See, you need to understand specifically if they are asking latent heat of fusion or freezing. Only these two are there in the syllabus. Okay, generally they are asking now solid changes into liquid, then the answer will be melting. If they go specifically like ice to water or water to ice, then the answer is different. That is what I told you earlier. Now for this question, answer is very simple, melting. Next, B. During the phase change means state to one state to other state, liquid to solid, solid to liquid, liquid to gas, anything. Okay, does the average kinetic energy of the molecules of the substance increase? So first we need to know what factor will affect average kinetic energy. Temperature. Temperature is the factor, only factor which affects average kinetic energy. But we know during a change of phase, temperature is constant. Correct. So during the change of phase from solid to liquid or liquid to gas, anything, any changes, temperature remains constant. And I told you average kinetic energy completely depends upon temperature. More the temperature, more the average kinetic energy. Less the temperature, less the average kinetic energy. But in this case, during a change of phase, temperature remains constant. So there will be no change in average kinetic energy. In this way you have to understand. Okay, so if you go to some other website, they'll give you no change in average kinetic energy and you don't know the reason. If they twist the same question in a different way, you will not understand. Why? Because you don't have the knowledge. That is the main advantage of watching videos from maths point of view. Here we are not giving you answer for this particular questions. We are training you in all the angles so that if the same question asked in different way, you should be able to answer. So in this case, temperature remains constant. That's why average kinetic energy remains constant. You can write it as no change or you can write it as remains constant. Next, what is the energy absorbed during the phase change called? During the phase change, there is a change in phase and energy is absorbed, correct? Solid is getting into liquid. Assume ice is converted into liquid, so it is absorbing the heat energy. What do you call that absorbing heat energy? That is nothing but latent heat. Okay, latent heat. That's it. During freezing also, during freezing it releases heat energy, right? That is also nothing but latent heat. So during ice to water, latent heat of fusion. During water to ice, latent heat of freezing. Anyhow, here they are going generally. That is why we are not mentioning freezing, fusion or freezing. If you write latent heat, that is. Our next question, state two differences between heat capacity and specific heat capacity. See, we have learned all the differences from the textbook in the theory concept video, correct? Now here they are asking for two. Okay, we will write 3 or 4. Okay, now listen, state two differences. First, always try to write the definition. We have learned the definition of specific heat capacity and heat capacity, correct? For both the side, okay, definition, write the definition. Then here, specific heat capacity does not depends upon mass. Does not depends upon mass. Why? Because specific heat capacity is for the unit mass. Okay, if I say a specific heat capacity of water is 4.2 joules per gram per Kelvin, that means the specific heat capacity for 1 gram of water. Okay, 1 gram or 1 kg. So it is always unit mass, but heat capacity depends upon, okay, it is exactly opposite. So specific heat capacity does not depends upon mass, heat capacity depends upon mass of the object or mass of the material. Then you can go for SI units. Okay, specific heat capacity joules per kg per Kelvin. Here joules per Kelvin. That's it. These are the differences, and we have one more sub question. Give a mathematical relation between heat capacity and specific heat capacity, that is nothing but C is equal to C dash by M. This is what we have learnt in concept video. Simple relationship. This is the formula to find heat capacity or specific heat capacity using any two variables. That's it. Our next question. A solid metal weighing 150 gram melts at its melting point of 800 degree Celsius by providing a heat at the rate of 100 watt. The time taken for it completely melt at the same temperature is 4 minutes. What is the specific latent heat of fusion of the metal? Specific latent heat, okay, of fusion. That means L, capital L we have to find. First we will write down what is the given data. Okay, now here mass is equal to 150 grams. Okay, then temperature is given. Only one temperature is given, that is 800 degrees Celsius. That is okay. Then okay, rate, okay, heat at the rate 100 watt. Watt is the unit of power, so power is given as 100 watt, and time is given as 4 minutes, but we know it should be in seconds, so 4 into 60. We'll keep it like that. Somewhere it can be easily cancelled or converted. What is the specific latent heat of fusion? So L we have to find. See, we know to find L, okay, what is the main formula? L is equal to Q by M. L is equal to Q by M, correct? This is the formula we need to apply to get the answer. But we have M, we don't have Q. But to find Q, we know, we have learnt in the numericals, we can use PT to find the Q. So Q is nothing but, see, P is equal to Q by T. This is the formula. Power is equal to energy by time, correct? Work done by time. Power is equal to work done by time. We know work done is nothing but the energy. Energy by time is nothing but power. So here we have power and time. To find Q, we need to send this on this side. So it becomes power into time by mass. What is power? Power is 100. Time 4 into 60 by mass. Mass, what is that? 150. So 0, 0. So 3 2s are 3 5s are. Then 5 1s are 5 20s are. So 20 into 4 into 2. What do we have? 20 into 4, 80. 80 into 2, 160. 160. We got the answer. What is the unit? Q by M. What is the unit of Q? Joules. What is the unit of mass? We have taken it as in gram. So joules per gram. That's it. Our next question. The temperature of 170 gram of water at 50 degrees Celsius is lowered to 5 degrees Celsius by adding certain amount of ice to it. Find the mass of ice added. Okay, this kind of question we have already solved once. Okay, I'll give you the formula as well as the substitution final answer. You have to calculate once, or else you will never get the answer. Now listen. See, first we'll write whatever given. The temperature of 170 gram of water. Okay, see, I told you earlier, hot object first. Okay, we'll take it as the first object, correct? So M1 is related to hot object. So here we are adding ice to water. Ice and water, which has high temperature. Okay, hot object or warm object, that is water. So mass of water, will take it as M1. M1 is equal to 170 grams. Then the temperature of 170 gram of water at 50 degrees Celsius. Water temperature is 50. So this is nothing but T1 is 50. Is lowered to 5 degrees Celsius. Sometimes they may confuse you. Lowered by 25 degrees Celsius or lowered by 30. Okay, assume now the present temperature is 50 and it is lowered by 30 degrees Celsius. By and to, you have to be very careful. Lowered to means whatever the value is given after, okay, lowered to, whatever the value is given, you can take it directly. Lowered by 30, assume lowered by 30. So initially it was 50, lowered by 30, that means 50 minus 30, 20 you have to take. So this lowered to, increased by, all those differences you should know. Okay, so here lowered to 5 degrees Celsius, so no problem. So this will be the final temperature that is 5 degree Celsius. Then what we are adding? Ice. We know ice temperature is 0 degree Celsius. So what are the things given? Specific heat capacity of water. So C is given, specific heat capacity. See, that is given in 4200 joules per kg. Joules per kg, but the value of mass is in grams. So this is where you have to be careful. If the specific heat capacity of water or all the specific heat capacity, latent heat, if all of them are in kg, this mass should be in kg. If all those specific heat capacity, say this is given as 4200 joules per kg per Kelvin, correct? And latent heat is given as 336,000 joules per kg. So here these two are in kg, so this mass should be in kg. If these two are in grams, this should be in gram. Anyhow, these two are in kg. You can convert this one, okay, into kg, or you can convert these two only to gram. Anything is fine. Okay, if you find, see here it becomes 4.2 joules per gram per Kelvin. This becomes 336. Okay, if you convert it. Now, if any way is always okay. If you get the correct answer, that is always good. So 170 gram is 0.17 kg. This you should keep in mind. Okay, now so here specific calorimeter, they are not talking about calorimeter, so we don't have to add that. So first, heat lost by an object is equal to heat gained by an object. That is the principle of calorimetry. Which object is losing the heat energy? Water. So everything related to water here, and RHS, everything related to ice, and after adding ice it melts. Keep that in mind. So here M1 CW T1 minus T is equal to mass of ice, specific latent heat, plus mass of ice, and so you can write it as I. Anything is fine. Specific heat capacity of water. Why we are writing specific heat capacity of water? Because this ice will convert into water later. Then that will be T minus T2. Okay. So here in both the case, M is common. So mass of ice. So L plus CW T minus T2. Then here it remains same. So we'll substitute all the values. M1 is 0.17 into what is CW? CW is 4200. T1 is 50 minus 5. Mi we have to calculate. So everything you send it this side. If you send this side, it becomes, it goes to the denominator. So L is 336,000 and plus CW, that is 4200 given. T, that is 5 minus 0. So, and Mi. See, till here you will get 2 marks. This question is for 3 marks. Till here you will get 2 marks because only in calorimetry substitution carries 2 marks. So if you substitute properly, then answer will be, if you calculate the answer, mass of ice will be equal to 0.09 kg or 90 grams. Anything is fine. You can write the answer in kg as well as gram. Final answer we don't care. If they specifically ask you to write it in SI unit, then 0.09 kg or 90 grams. That's it. Now we'll move on to 2019. State whether the specific heat capacity of a substance remains same when the state changes from solid to liquid. Give an example to support your answer. We know this question we have learnt in one of the questions just now in the same video. The same questions, okay, no change in the question and answer remains same. That is why we are skipping it here. Our next question, define calorimeter, name the material used for making calorimeter, and we have one more sub question. First we'll go for the first one. Okay, define calorimeter. Calorimeter is a cylindrical vessel which is used to measure the amount of heat energy gained or amount of heat energy lost by an object when it is mixed with the another object. So see, when you add ice to water, ice will get melted, correct, because it is absorbing the heat energy from the water. How much heat energy is absorbed by the ice, or how much heat energy is lost by the water? Okay, that is what we are going to find using the calorimeter. meter. So one object is mixed with the another object, how much heat energy gained or lost, that one we are going to find using the calorimeter. Then name the material used for it. It has to be copper because it has less specific heat capacity. So not just copper, it is thin copper vessel. Next, why the calorimeter made up of thin sheets of the above material mentioned in second question. Okay, in second question we have mentioned we have to use copper and it should be thin copper. Why it has to be thin copper? That is their question. If it is thin, its specific heat capacity will be less. Specific heat capacity will be less. Here specific heat capacity or heat capacity, both are okay. You can write anyone. Okay, so it will be less. If it is less, it absorbs less heat energy from the liquid or mixture. Our next question, the specific heat capacity of substance A is 3800 joules per kg per Kelvin and of a substance B 400 joules per kg per Kelvin. Which of these two substances is a good conductor? Justify your answer. Okay, first we need to know very good conductors will have less specific heat capacity. We have discussed this one earlier. Poor conductor of heat will have more specific heat capacity. So here they are looking for good conductor. Good conductor will have less specific heat capacity. So which one is that? 400 joules per kg per Kelvin. So substance is okay, which is a good conductor. Substance B. If you write just B, that is always fine. Or B in the bracket if you want to specify joules per kg per Kelvin, this is also fine. For this one you will get 1 mark. They are asking for the reason. Our next question, the melting point of naphthalene is 80 degrees Celsius and room temperature is 30 degrees Celsius. That will write it down. Okay, melting point. Okay, for now just will write it as MP, but you should not use any short forms in the exam. That is 80 degrees Celsius and room temperature. Okay, room temperature is 30 degree. This is mentioned. Next, a sample of naphthalene liquid, a sample of liquid naphthalene at 100 degrees Celsius is cooled down to room temperature. So initially it is at room 100 degrees Celsius. So naphthalene, okay, for this is initial temperature is 100 degrees Celsius. It is cooled down to room temperature. Draw a temperature time graph to represent the cooling, and the graph mark the region which corresponding to freezing process. So here a few students will get confused. First we'll write the axis. Okay, here temperature. Okay, here time. This is the graph they are asking for, correct? So few students will get confused here. Why? Because they are given melting point and they are asking us to mark the freezing process. Okay, melting point is given. What is melting? Ice to water. You can take anything. Okay, just for an example, ice to water melting. What is freezing? Water to ice. They have given melting point and they are talking about freezing. And we know, see, this is what important. So when it comes to calorimeter, we have understood that for pure materials, okay, pure liquids or pure substances, melting point is same as the freezing point. Keep this in mind. So if they are given melting point and they are talking about freezing, that means freezing point is nothing but the melting point. Keep this in mind. This is very much important. Many students will get confused here only because of this concept given data. They will not even select the question. This question is for 3 marks. Very easy way to get the marks. Okay, so they have given 3 temperatures: 100 degree, 30 degree, 80 degree. So we know temperature increases. So this is 100 degree, somewhere here 80 degree, and here 30 degree. Done. So marking is done. We don't have to mention the time. That is always fine. Now initially it is at 100 degree. Correct. So it is cooled down and brought to freezing point. After freezing point, it has come to room temperature. So what is the freezing point? 80. See, this one is very much important. Initial temperature, naphthalene 100. So it has gone to freezing point. Freezing point is nothing but the melting point. Keep this in mind. Melting point and freezing point. What is melting? Ice to water. Freezing, water to ice. But for few pure substances, melting point is same as freezing, and in this question they are talking about freezing. So these two are same. So now initial temperature is 100, it has freezed to 80, then brought to 30. So here while drawing it you have to be very careful. So it is brought to from 100 to 80, then freezing, then it brought to 30. So here you have to be very careful. How I draw this graph? See, this slant line downwards represents temperature is going down. Correct. Why we have to write a horizontal line? Horizontal line means what? So there is a change in phase. Keep this in mind. So they are talking about freezing, right? Freezing is a change in phase. We know during the change in phase, temperature remains constant. So in order to maintain the temperature constant, it has to be horizontal, or else you can keep in this way, okay, in your mind. Whenever there is a change in phase, there should be a horizontal line. This slant downward tells us temperature is reducing, but and they have mentioned freezing, correct? Freezing process at 80° it freezes. So freezes means there is a change in phase. During a change in phase, temperature remains constant, so horizontal. After some time it reduces to room temperature. This is where you have to be very careful. Okay, somewhere you may get confused, just go back and rewatch it. You will definitely understand if you have the confusion, or else it is very simple. See, if it is going up, that means temperature is increasing. While going up, if you see a horizontal horizontal line, that means there is a change in state of matter. So here also, while going up or coming down, a horizontal line means, okay, there is a change in phase, and they ask us to mark the region of freezing. This is there, it is freezing. That's it. 3 marks if you have the proper knowledge. Our next question, 104 gram of water at 30°C. See here, this question is exact replica of the last question, 6th question in 2017. Only the values are different. The method, everything remains same. So here they're again asking for mass of ice added. The same question, they have given specific heat capacity of water, specific heat capacity of calorimeter, and latent heat of fusion. Everything is given. Mass of ice we need to calculate. This is the same question in which we have discussed earlier, 2017. That answer I have given. The same method, only the values are different. That's it. That is why we are skipping this question. Now we'll move on to 2020. The diagram below shows the change of phase of substance on a temperature versus time graph on heating the substance at a constant rate. So here it is clearly mentioned in the graph they are going to heat the substance at a constant rate. Okay, then see the question, why is the slope CD less than the slope AB? That is one question. Next question, what is the boiling and melting point of substance? They are asking about boiling and melting point of substance. So here, to boil, first the object has to be melted. To melt, that is nothing but it is freezed. See, it is freezed, then it melts. After it melts, then we can bring it to boiling point. Correct? This is the order. So this is how we need to understand the graph. First, it is freezed now. From freezing, it has to melt. From melting, it has to go to boiling point. This is the process, and using that we can easily analyze the concept. Assume now we are talking about some ice. Okay, ice at -°C, -degree, or anything, any object. Now see, if you see a slant line, okay, slant line, okay, slant up, okay, inclined line, that means increase in temperature. It's going up. If the graph is like this going down, okay, then slant line represents temperature is reducing. Now the graph is going up, so the slant line, it is nothing but increase in temperature. And in the previous question we have learned that horizontal line means there is a change in phase. Correct? There is a change in phase. Here one horizontal line, here one horizontal line, that means there is a change in phase. So this slant line represents increase in temperature. Now see, so here this is the graph, that is what we have understood. Now why is the slope CD less than slope AB? Here you need to understand slope AB, okay, this slope, okay, is greater because why? Because it has taken less time to come to the change in phase. Here can you see, here it has taken more time to come to the change in phase. Here it has taken less time. So less time means the slope will be more. This is one way to understand. So here we are not answering the question. We are understanding the concept. If the time is less, slope will be more. If the time is more, see from here to C to D, it has taken long time. That's why the slope is less. But now the question is why? Why is the slope CD less than slope AB? We got to know AB has more slope than CD, but they are asking for the reason. Very simple reason. If the slope is more slope means low specific heat capacity. If the specific heat capacity is low, slope will be more. Keep this in mind. Okay. So answer for sub question A, AB. Okay, AB slope is more. Correct. Slope is more because it has low specific heat capacity. Low specific heat capacity, or capital C. Capital C is the symbol for specific heat capacity. You should never use symbol or these short forms in the sentence. Always you have to write it in expanded form. AB has more slope, that is given in the question. Why slope CD is less than AB? That means AB slope is more. Why? Because it has low specific heat capacity. If the specific heat capacity is low, slope will be more, and the CD has less slope. Correct? Less slope because it has more SHC. Keep this in mind. This is the reason. This is very, very important. Then, what is the boiling and melting point of the substance? We have understood this is melting and this is boiling. Melting point. What is melting point? The temperature at which it melts. Correct. Melting point means the temperature at which it melts. So, at what temperature is melting? That is T1. Melting at T1, boiling at, see, boiling is started at T2. If they have mentioned, okay, degrees, okay, 30 degree, 100 degree, you have to write those degree values here. Anyhow, it is mentioned T1 and T2. That's why I am writing T1 and T2. If they have mentioned 30 here, you mention 30 here. If any degree, any value, 180, you write it here. That's it. So understanding, if you understand the concept, then these kind of questions will be very easy, because when it comes to calorimetry, if it is graph related question, if you don't understand it properly, you will definitely skip in part B. Correct? So in part B, it is choices. Other two questions are easy. Only this question you may face problem. But if you know this one, you can aramse get the marks within few minutes. 3 marks, 3 to 4 marks in very few, within 1 minute you can get if you have the knowledge. Just by seeing the graph only, we need to understand. See, first it is melting, then boiling. Done. So increase in temperature. So these are increase in temperature. So here temperature remains constant. Based on these things, okay, these simple things only, they are going to play a game with you. If you have the knowledge, you can aramse answer any question. Our next question: why does a stone lying in the sun gets heated up much more than the water lying on the same duration of time? So now listen, there is a water and stone, both are there and they both are exposed to sun, and they are saying stone gets heated up very faster. Okay, much more heat. Okay, stone will get much more heat than the water. Why? Very simple. We know good conductors of heat as low specific heat capacity. Stone is a good conductor of heat. We are not talking about electricity. Conductor is not always about electricity. It is always about both heat as well as electricity. Here we are talking about heat. So stone is a good conductor of heat. So it has low specific heat capacity. This is the reason. Okay, water is a poor conductor, so it has more specific heat capacity. So what is the reason for this question? Stone has very low specific heat capacity, that's why it gets heated faster. Our next question: two metallic blocks P and Q having their masses in the ratio are supplied with the same amount of heat. Okay, if their temperature rises by same degree, compare their specific heat capacity. So there are two metallic blocks. Okay, P and Q. Okay, these are the two metallic blocks of their ratio, mass ratio. Okay, this is m1, okay, mass of P and mass of Q. Okay, they are in the ratio 2:1. Mass of P is 2 times the mass of Q. That means if mass of Q is 1 kg, mass of P is 2 kg. This is the concept. Now heat supplied, okay, heat energy given for both the metallic blocks are same and temperature rises by the same degree. Okay, now compare their specific heat capacity. Now few students will get confused. First I'll teach you the answer, okay, then I'll teach you that confusion point. Okay, now listen. We know specific heat capacity is Q by m delta T. Q by m delta T, correct? They have clearly mentioned Q and delta T. Q means heat energy supplied and change in temperature, both are same. Both are same. So now it is only related to specific heat capacity and mass. How these two are related? These two are inversely proportional. Inversely proportional. That means the metallic block which has more mass will have less specific heat capacity. This is the concept. Okay. Now, so we'll go for specific heat capacity of P and specific heat capacity of Q, that is 1 by mq. Why Q and delta T is not written? Because these two will get cancelled, correct? So or else you can write it directly here, and we know we want to find the ratio of their specific heat capacity. So ratio is nothing but division, right? So Cp by Cq, what is Cp? Q by mp delta T, and here Q by mq delta T. So there are two fractions. First one I'll write it as it is, and second one, instead of writing the division, okay, I'll write the multiplication. I'll take the reciprocal, mq delta T by q, correct? Q get cancels, delta T get cancelled. So what do we have? Cp by Cq is equal to mq by mp. So what is mq? That is 1. What is mp? That is 2. So it is 1:2. 1:2. Okay. So if you listen, you don't have to do all these things in the exam. If you know the concept, you can say right. First thing you need to know, these two are inversely proportional. Inversely proportional means, so if the more mass, it will have least specific heat capacity. That you should know. If you know that, you can just interchange this one. Okay, you will get the answer. Now, what is the doubt? We know specific heat capacity does not depend upon the mass, correct? Now in this question we have proved that it is 1:2. That means more the mass, less will be the specific heat capacity. But we know specific heat capacity does not depend upon mass. Okay, this condition only valid when we are talking about two same kind of object, same material. Okay, see, specific heat capacity will not change. They will remain same. Specific heat capacity of two different objects remains same only when they are identical objects, same objects. In this question it is not mentioned. Identical objects are both P and Q are made up of same metallic blocks, correct? So if both are of same metallic blocks or identical metallic blocks, specific heat capacity remains same. Okay, even though mass changes, specific heat capacity will remain same, 1:1. Both will have same specific heat capacity. But in this question, they have not mentioned both P and Q are of same material, so they will definitely have different specific heat capacity. So this is the advantage of watching videos from maths point of view. Okay, so if you go to some website, you will get 1:2 directly. But these conditions, who will teach you? This knowledge, where will you get it? Someone has to teach you. That is what we are doing. That is the main advantage. We are not just learning the answer. We are learning the answer in all the angles, so that whenever the same question is twisted in different way, you should be able to answer. Our next question, define heat capacity of a substance. What is the SI unit and what is the relation between heat capacity and specific heat capacity? The same question we have discussed earlier, correct? So the definition SI unit, what is the relation between C and C dash? C dash is heat capacity, C is specific heat capacity. This one we have already learned, that is why we are skipping this question. Now we'll move on to 2023 thermal capacities of a substance A and B are same if mass of A is more than mass of B. So these are the given data. First we'll write down C dash of A and B are same. Thermal capacity. What is thermal capacity? Heat capacity. Okay. Then mass of A. Okay. Mass of A is more than mass of B. Mass of B. Okay. So these are the given data. Now we'll go for the question. Which substance will have more specific heat capacity? See, first before answering this question, first understand this one. When the specific heat capacity of two objects will be same, when it will be same, when both are same material. So okay, when the both are same material, then specific heat capacity is same, correct? But here in the question it is never mentioned both the materials are made up of same materials, so specific heat capacity will be different. Now in one of the previous question we have learned that specific heat capacity is inversely proportional to mass. More the mass, less will be the specific heat capacity. So here which one has more mass? A, that means it has less specific heat capacity. Which has less mass? B, that means it has more specific heat capacity. What is the question? Which substance will have more specific heat capacity? So answer for A, right? A. Okay. B. If you write just B, you will get 1 mark. Okay, material B, substance B. If you write any, just B is important. So if you write B, substance B, it is also correct. Now we'll go for second question. Which substance will show greater rise in temperature if the same amount of heat is supplied to both? Okay, now they are supplying same amount of heat, okay, to both the objects. Now which will show greater rise in temperature? See, when it comes to specific heat capacity, we know it depends upon mass sometimes, and sometimes it does not depends upon mass. When they both are made up of same material, it does not depends upon mass. And if they are made up of different materials, then it is inversely proportional to mass. So in this question it is not mentioned both are of same material, so it is inversely proportional. In the same way, when it comes to heat capacity, we should know something. Okay, so when the heat capacities are same, when the heat capacities or thermal capacities are same, so both will have same rise in temperature. Both will have same rise in temperature. Now we got to know both will have same rise in temperature. Why? Because thermal capacities of both the objects are same. Our next question, a piece of ice of mass 60 gram is dropped into 140 gram of water at 50 degrees Celsius. So now there is a water, and for that we have added a piece of ice. Now we know that after some time the temperature reduces as well as the ice also melts. Calculate the final temperature of water when all the ice has melted, assuming no heat is lost into the surrounding. Specific heat capacity of water, latent heat, everything is given. So what we need to find? We need to find the final temperature. Okay, so we need to find what? Final temperature. This is the final temperature symbol we use. Correct. We know we always assume the warm or hot object as the first object. So here we are adding ice to water. Ice and water, which is warmer? Water. So that will be our first object. So if you follow this procedure, there will be no confusion about M1, C1, all those things. Okay. So M1, mass of water is 140 gram. Then temperature, okay, it is a temperature 50 degree. Then mass of 60 grams of ice, so that is M2, 60 gram, and temperature we know ice is 0 degree Celsius. Then specific heat capacity of water is 4.2 joules per gram per Kelvin, and specific latent heat, that is L is equal to 336 joules per kg. Joules per kg, not kg, gram. Okay, per gram. These are the given data. We know in the this one concept video I have given you direct formula for final temperature, correct? So final temperature formula, see, first I'll write you the actual formula. Okay, M1 CW T1 minus T, this is the simplest formula we have learned, right? ML, this is for ice, mass of ice, or M2, then M2 CW T minus T2. Okay, here this is the main formula, correct? So here we need, what we need to find, M1 CW. Okay, so we have to find the final temperature. See, final temperature, finding that you have to go through, we have to transpose many things and get the solution. That is what we are going to do. Listen, we know all these values, correct? Except T, we have everything, correct? So instead of substituting it here, first we'll get the final equation, then we can substitute it. Okay, so to find this value, first we have to multiply these two here and M1 CW to T also, these two with this one, and again multiply with this one. So this becomes M1 CW T1, okay, not bracket, T1 minus M1 CW into this one, M1 CW final temperature is equal to, no change in M2 L. Now again we have to do the same thing with these two terms. First we will multiply these two with T, then with T2. So M2 CW T minus M2 CW T2. Okay, so what we need to find, final temperature, that is nothing but T. So send these T terms one side and remaining things on the other side. Anyhow, this is positive and this is negative. If you send this one on the right hand side, it becomes positive. So I'll send this term on the right hand side and remaining these two terms, M2L and M2CWT2 on the other side, so that final temperature will be on one side and remaining things will be on the other side. So here M1 C1 T1, no change. I'm going to send M2L and M2CW and T2 here. So minus M2L plus M2CW T2, and I'll send this one on the other side. So here we already have M2CWT, this minus becomes plus, and this one M1CWT. Okay, now in these two we have T common, correct? We have T common, and so this becomes T is equal T, if you take T common, M2CW plus M1CW, correct? Now we need final temperature, we'll send this one this side. So the final this equation will be M1CWT1 minus M2L plus M2CWT2 divided by, if you send these two this side LHS, this becomes M2CW plus M1CW is equal to T. Okay, here if you substitute the values, we will definitely get 11 degree as the answer. So T is equal to 11 degrees Celsius you are going to get. See, all these values are there, correct? M1 CWT1, M2L and M2 CWT2. So here you have to be very careful. T2 we know it is 0, so anything multiplied by 0, this complete term will go up, correct? So we have this term and these two terms, all these values are here. Just substitute it and calculate it, you will definitely get 11 degree, because I have tried it, because we don't have much space. And see, these circles you have to do it in exam, or else you can by heart this final temperature formula if ice is given. If ice is not given, final temperature formula is only this much. See, if ice is not given, okay, assume ice is not given, minus M2L will not be there. remaining everything will be there. This is the final temperature. Assume instead of ice they are putting this one iron piece into water, anything, okay, except ice. Okay, here because of ice we are getting latent heat. If the ice was not there in the picture, if any other substance is there, minus M2L, only this one will not be there, everything is same. Okay, so this is the final temperature formula. Substitute the values, you will definitely get it properly. Now we'll move on to 2024. In that first question, why does it becomes pleasantly warm when the lake starts freezing? What happens during freezing? During freezing, it releases heat energy. It releases heat energy. During melting, it absorbs heat energy. So if it is melting, it absorbs heat energy from the surrounding. So heat energy is absorbed from the surrounding. That means temperature of the surrounding goes down. Now it is about freezing. When it is about freezing, it releases heat energy. When it releases heat energy to the surrounding, okay, the surrounding becomes warmer. That is the answer for this question. Second one, sub question B, water freezes to form ice. So it is from water to ice. There is a change in phase. What change would you expect in the average kinetic energy of the molecules? During a change of phase, temperature remains constant, and we know average kinetic energy depends only upon temperature. Now during a change, temperature is constant, so the average kinetic energy also remains constant. There is no change in kinetic energy. A is done. Okay, B, okay, remains same. Remains same. Then sub question C, we have one more. Which will contain more heat energy, 1 gram of ice or at 0 degree, or 1 gram of water at 0 degree? First you need to understand, always water will have more heat energy than ice. At the same temperature, water will have more heat energy, okay, and ice will have less heat energy. Okay, keep this in mind. So answer for this one is 1 gram of water at 0 degree Celsius is the answer. This is the answer, but we need to learn something about this parts sub question. See, because the same question can be twisted in different ways. Now we got to know from this answer, water at 0 degree Celsius, don't worry about gram, water at 0 degree Celsius has more heat energy than ice at 0 degree Celsius. Correct. Assume we have two juice bottles of same quantity. Okay, both have same quantity. Now we have to cool it down. What I'll do, I'll put the juice bottle A in ice cold water at 0 degree Celsius, and juice bottle B, I'll put it in ice surrounded by ice cubes. We know ice cubes have less heat energy, so it absorbs more heat energy from the bottle. So bottle gets cooled down when it is surrounded by ice cubes than ice cooled water. Why? Because ice cubes have less heat energy, so it absorbs more heat energy. Once it absorbs more heat energy, this bottle, if you absorb more heat energy from it, it becomes cooler. Correct? So that is how they can form the questions, okay, using this concept. So always keep in mind, 1 gram of water at 0 degree Celsius will have more heat energy than 1 gram of ice at 0 degree Celsius. Don't worry about gram. Okay, ice will have less energy at 0 degree. Ice cold water, okay, at 0 degree Celsius will have more heat energy. Keep this in mind. Our next question, how much heat is required to convert 500 gram of ice at 0 degree Celsius to water at 0 degree Celsius? The latent heat is given. See, mass is given, latent heat is given. They are asking about heat energy, how much heat is required. Q we need to find. Correct. Q we need to find. Mass is given as 500 grams. Latent, okay, heat of fusion is given, and that is 330 joules per gram. Okay, here whether you have to convert this gram into kg or we have to keep it like that, so that will get the proper answer. See, that always depends on specific latent heat. Okay, in this question we are talking about specific latent heat. In previous questions and all, we used to talk about specific heat capacity. So whether we have to convert into kg or keep it in gram depends upon specific latent heat or specific heat capacity. See the unit. it is in gram, so this has to be in gram. If this is in kg, this should be in kg. Okay, or else everything will become wrong. Now both are in gram, no need to convert into anything. And we know, see, L is equal to Q by M. We need Q. Q is equal to ml. Mass 500, L 330. So the final answer, see, final answer will be 165,000 joules. That's it. You don't have to convert into 165 kilojoules and all. If you keep it like this, you will get full marks. Our next question, 85 gram of water at 30 degrees Celsius is cooled down to 5 degree by adding certain mass of ice. So we are adding ice to water. So initial temperature of water is 30. Now it becomes to 5 after adding some mass of ice. Find the mass of ice required, specific heat capacity and specific latent heat, everything is given. So we'll write down everything. So here again, first object will be the warmer object or a hot object. We are adding ice. Ice is cold object. So warmer object is water. We'll take object 1 as water. So mass 1 is 85 gram. Then it is a temperature T1 30 degree. Now it has cooled down to final temperature is 5 degrees Celsius. We are adding ice. So ice is the object 2. Its temperature is 0 degrees Celsius and we have to find M2. That is the question mark. CW is given as 4.2 joules per gram per Kelvin. Then L is given as 336 joules per gram. Now here mass of water and mass of ice we are going to find. Mass of water, whether we have to convert into kg or keep it in grams only, that depends upon specific heat capacity. See the specific heat capacity, it is in grams, right? So let it be in grams. If the specific heat capacity is in kg, this should be converted into kg. Now both are in grams, so no issue. What is the formula? M1 CW T1 minus T is equal to ml. M is nothing but mass of ice, that is M2, plus this ice will melt, right? Once ice is melted, the same mass will be converted into water. That is why specific heat capacity of water, and this is T minus T2. Okay, so here what we need to find? M2, correct? So here M2 is common, we take M2 as common, it becomes L CW T minus T2. Here everything remains same. So we want M2, send everything this side. M1 CW T1 minus T by L plus CW bracket T minus T2. This type of question we have already solved twice. Again we are solving it. Just substitute all the values. Then what is M1? 85 into 4.2 into initial temperature 30 minus 5 by what is L 336 plus CW 4.2. This will be 5 minus 0. So if you this is the substitution. For this one you will get 2 marks. If you if you calculate the answer, the mass of ice will be 25 grams. That's it. Now we'll move on to 2025. In that first question, a certain amount of heat will warm 1 gram of material X by 10 degree. Okay, material X. Okay, this is a question sub question here, right? Material X, okay, rises by 10 degrees Celsius and material Y rises by 40 degrees Celsius. This is the given question which has higher specific heat capacity. See, they are giving same amount of heat energy. Listen, so we know in one of the question we spoke about stone and water. If you keep stone and water, okay, in front of sun, which will get heated faster? Stone compared to water. But we have learned that which will get heat energy faster, which object temperature rises faster, that object specific heat capacity is lower. Okay, specific heat capacity of an object will be less Okay, when it increases its temperature faster, in a faster way. So here, which has increased in a faster way? 40 degrees Celsius. Correct. So, and if this has if increased faster way, that means its specific heat capacity is low. If this is low, obviously this is high. This is how you have to decode the answer. So again, understand, if an object gets heated faster, if the temperature of an object rises rapidly, that means it has low specific heat capacity. So these are the facts, you have to write it somewhere, so that these kind of questions, they will create these kind of questions only. If you know all the facts, you can easily answer them. If the temperature rises faster, that means it has low specific heat capacity. In this question, they are asking the which material has higher specific heat capacity, that is material X. What is the answer? So you don't have to write all these things in the exam, you just write X. Not, you don't have to write material X, you just write X, you will get marks. So sub question A is done. We'll go for sub question B. Which material X or Y would you select for calorimetry? Okay, calorimeter. In calorimeter, we know, okay, it should have low specific heat capacity. That's why we choose copper. Correct. Copper and water. Okay, copper and different material. Why we have to select copper? Because it has low specific heat capacity. So we got to know here, material Y has low specific heat capacity, so material Y. That's it. You just write Y. So you don't have to write material Y has to be selected for calorimeter. All those dramas not required. Just write Y, you'll get full marks. One mark question, one letter, done. That is where physics is completely different from other subjects. So here, for most of the questions, if you write just words or letter, you will get full marks. Okay, we have one more sub question. The specific heat capacity of a substance remains same when it changes its state from solid to liquid. State true or false. They are just asking true or false. We have to write just true or false. We have learned that specific heat capacity will not remain constant when there is a change in phase or change in state of matter. So it is clearly mentioned solid to liquid, that is change of state of matter. So specific heat capacity will definitely change, it will change. So in the question it is mentioned that it will remain same, so this is false. That's it. Our next question, calculate the amount of heat energy absorbed by 200 gram of paraffin wax to melt completely at melting point. Okay, specific latent is given. Very simple question. See, heat energy we need to find. Mass is given as 200 grams, and specific latent heat. Don't worry about the materials, they may use paraffin, naphthalene, anything, just worry about the data. So specific latent heat is given as 146 joules per gram. See, this is also in gram, this is also in gram. We can say go for the calculation without converting it. Okay, we know L is equal to Q by M. So Q is equal to ml. M is 200, L is 146. So if you multiply these two, answer will be 29200 joules. That's it. Our next question, 30 gram of ice at 0 degree Celsius is used to bring down the temperature of certain mass of water at 70 degree Celsius to 20 degrees Celsius. Find the mass of water. Specific heat capacity of water is given, specific latent heat of ice is given. See, in previous question and all, okay, they used to ask to find the mass of ice. In this question they are asking us to find the mass of water. See, what is the formula? M1 Cw T1 minus T is equal to, we are adding ice, right? M2L plus M2 Cw T minus T2. Correct. This is the formula. Here everything is given except M1. So to find M1 is equal to M2L plus M2 Cw T minus T2 divided by Cw minus T1 minus T. So see, this is the formula. Here M1 is the mass of water, specific heat capacity of water, initial temperature of water, final temperature, everything is given. Correct. And mass of ice, specific latent heat is given. Mass of ice, again the same thing, specific heat capacity of water, final temperature and initial temperature of water, there's one ice, that is 0 degree. Everything is mentioned, just substitute it, you will definitely get the answer. The final answer will be 6 gram. Okay, that's it. Now we have finished calorimetry previous year questions. So in this way, if you can understand, you can aram se learn it. Now listen, this is how you have to learn concepts. Okay, concept videos, theory solutions, and numerical videos, all these are in the description box. Once you get the knowledge from the textbook, understand how the previous year papers are completely questions of previous year papers are completely different from textbook. Once you understand that, now you know the difference, but you don't know whether you are ready for board exam or not. That is where we are going to create logical and application based question paper. That will be that video will be available in the description box, and the PDF is also available in the description box. What is that PDF is about? That PDF is created by taking the questions chapter wise, again only about calorimetry. Okay, only about calorimetry. The questions are taken from specimen papers of ICSE physics over the years, and since ICSE has released one CBQ competency based questions paper, from that only based on calorimetry we have selected these questions, and the answer for these questions are also available in the description box. The name of the video is logical and application questions based on every chapter. It is again chapter wise, only from force, only from work done questions. All these questions are chapter wise. So once you learn this one, textbook knowledge, then previous year papers, then logical and application questions only based on one particular chapter, so you will be very strong in that particular chapter, so you can answer any kind of questions. That is why about every chapter you have to learn in this way to get complete knowledge, so that you can answer any question in the board exam with the confidence. Thank you.